Thank you very much to the organizers for giving me the chance to present the work and the machines that I will tell you about today. I work at QuEra Computing, and at QuEra we build neutral atom-based full-stack quantum computers and make them available for the world to use. Today I will be talking about the particular machine that we have available for the world to use through Amazon Ri-Cat. It's a cloud service that has a bunch of different quantum hardware on it. And in particular, Aquila is an analog mode quantum computer. It's a Hamiltonian simulator, so that means that you're programming the Hamiltonian that controls the resolution of the system. I will first tell you about how the machine works and how you could use it yourself, and then I will tell you about two stories of manipulating quantum phases on that machine. And these are stories that were basically collaborations with academic groups. So first of all, what are neutral atoms? As qubits, you take individual elements from the periodic table, you put them into optical potentials, you can move those objects around, so you can actually configure or assemble your processor by manipulating these optical potentials, and then you build the quantum information into the internal degrees of freedom of these atoms, and in particular by taking these atoms into these highly excited Rydberg states, you can get them to interact with each other. Just in case Hannes didn't convince anybody that neutral atoms are cool, I want to give you a few reasons to be excited about them from my perspective. So the first one is it's a very versatile quantum playground. Okay? It's powerful both for analog and digital quantum computation. You get to program what the processor looks like in front of you by just defining these optical potentials. You don't rebuild or reprint a different kind of processor. You just you work with the same system, and you can explore many different architectures with it. The connectivity can be all-to-all, and that is not something that Hannes talked about today, or I will talk about. But actually, by moving those qubits around in the middle of the coherent evolution, you can actually create all-to-all connectivity, and that's going to become the basis for a digital-based kind of fault-tolerant quantum computer based on neutral atoms that's coming out. And finally, it's a system where you can actually have different kinds of qubits for different kind of functionalities. You can have a Scylla-type qubit, a data-type qubit, by combining different species of atoms, or even taking different levels inside an atom and using them for different purposes. So these are kind of fantastic knobs to use in a quantum playground. Second reason to be interested in neutral atom quantum computers is that with the architecture that we have today, with the kind of physical technology that we have today, we can scale to about 10,000 qubits without kind of any major technological limitations, while keeping, fundamentally keeping the performance in terms of coherence not degraded with the size of the system. And I just want to point your attention to these two seminal papers in the last year, or in the last 2 years, I guess, that have shown how the system can scale to large size, thanks to this shuttling approach, which allows you to do scalable wiring of your qubits. So again, this overall connectivity, and in addition to being able to address your qubits along the z dimension through just a projection of optical light. And demonstration of these state-of-the-art 2-qubit and single qubit fidelities, which are so close to the fault tolerance thresholds that now we can actually imagine scaling the system and having logical qubits that basically stay at the level of fidelity that you need to do something useful in the limit of very large systems. It's a platform that has caught up very quickly with many other quantum computing platforms, and it's an exciting time for it. Then I want to give you 2 reasons to care about Aquila specifically, which is an analog, which is our analog computer. First of all, the Rydberg Hamiltonian, which Hannes also described for you, is actually pretty powerful for encoding all kinds of problems, both of the native and the non-native type. So the native type is the images graph that you started with, and the non-native type is the kind of arbitrary graphs that you can encode now using these kinds of crossing gadgets and so on. then on Aquila, you actually get that ability that I kind of tried to describe to you of configuring the qubits for the problem at hand. And we like to call this ability the FPQA, like field programmable qubit array, in analogy to the classical FPGA. For those of you familiar with that technology in classical computing, it enables the user to configure the classical resources on the computer to be optimal for the problem. And in the same way, by manipulating where the qubits are, you can actually construct the architecture in a way that either encodes the problem or is optimal for the problem at hand. And that's pretty powerful in this regime of analog computing. And then one thing that I will talk about is the ability to both do kind of adiabatic and diabatic type algorithms on the system, as well as hybrid classical processing that lends itself well to all kinds of variational problem solving, variational fun algorithms. And then finally, and I think I want to convince the most important and should be the most exciting thing to you is that this quantum playground is actually available to you. So if you want to go around, play around with this, go and play around with this Rydberg Hamiltonian, you have access to it through the cloud. So it's accessible to anyone on Amazon Bracket. It's, as of last week, available 100 hours per week, and that's 60% of 24/7. So basically, most times that you walk up to use the machine, you can actually send jobs in, get data back right away, and learn very quickly the parameters for the project that you might want to pursue on Aquila. You have control of up to 156 qubits that can be arranged into nearly arbitrary arrangements. And for those that have one special parameters, we're actually very happy to work directly with people on special projects to help push the system in one direction or another in order to enable, to open up interesting use cases. So come talk to us if you want to do something special that isn't possible to do with the constraints of the cloud service. So what kinds of things can you do with this type of machine? Well, first of all, and Hannes alluded to this, there's a long trail of trailblazing achievements from a machine that is basically a precursor to Aquila, which is what we have in mind. That was the first machine at Harvard that made significant discoveries and interesting observations in kind of everything from observing spin liquids to preparing quantum many-body phases and observing spars and many-body dynamics. So all of these kinds of things are things you can do in Aquila. And in particular, here's a sampling of projects that we're working on right now, QuEra with a bunch of collaborators. Just a couple of things to highlight. There's a lattice gauge theory project with collaborators from Innsbruck over here. We're working on quantum machine learning and trying to benchmark the performance of Aquila on a kind of quantum machine learning algorithm against digit recognition data set. And then the thing that I will talk about today, actually, I will focus on the critical phases, and this is a project that's wrapping up. And it's basically preparing an incommensurate phase on a ladder of atoms that's been predicted and found in theory, and now we're able to observe it by probing an incommensurate ordering on an array of atoms. So that's going to be part 2, and then part 3 will be showing some tricks of circumventing this gap closing problem as you try to prepare these hard many-body states. And this has to do with trying to do that kind of shortcuts to adiabaticity type protocols, and utilizing many-body dynamics following a quench. But before I go into those two kind of special projects, I do want to tell you a little bit about how Aquila works under the hood and how you could use it if you were to go online and try it. So that's part 1. This is the same Hamiltonian that Hannes talked about at length. Okay, and here it is again at full glory, and this is the Hamiltonian describing the Rydberg system, and you directly program the parameters in this Hamiltonian as functions of the function of time. So you have as close to programmable control to hardware as you can get. Essentially, you basically you are an experimentalist accessing the hardware without having to build it. Okay, and the terms are basically first one is the energy cost that you get when atoms are too close and both try to be in the Rydberg state. And that term is programmed essentially with the positions of the atoms by setting their coordinates in 2D. The second term is the drive term, so the laser that drives the atoms from the ground to the Rydberg state. The Rydberg state, again, is the one where the atoms interact. You can control the laser intensity and phase. And then the last term is the detuning between this drive laser and the qubit resonance, and you can think of it as an energy cost function. And so in thinking about what the result of your computation would be like, you have to kind of think about the relative scale of these terms. And the Rydberg blockade, that is a very useful kind of abstraction to think about, essentially tells you that two qubits cannot be both in the Rydberg state if the first term is larger than the amplitude of the drive, which is the second term, and the detuning of the drive, which is the last term. And so the way to think about programming these terms is, the first term is you're programming qubit connectivity in your problem. The second term is basically setting the algorithm that's going to find your solution. And then the last term is kind of like an energy cost function. There's another term coming soon. This is not available yet, but that might be exciting to some people because it starts to provide some level of local control, and that is basically local detuning control, local cost function. And I think actually Jonathan Pritchard is going to talk about some of the stuff in their system. Now I talked about programming as well Hamiltonian, and in most cases you have to think about the whole Hamiltonian, but it's also useful to think about kind of doing two parts of that. The first part is arranging qubits, and you arrange them once and they stay arranged in that position during the coherent evolution of the system, and that's this FPQA concept. So you basically set the architecture of your processor or encode your problem. And then the second part is where you control the drive. It can be kind of an arbitrary waveform, and that's the part which decides whether you're doing an adiabatic annealing protocol or a diabatic protocol or digital pulses like in the QA way. And so it's helpful to think about these two ways of two steps in specifying the program that runs on the machine. So now let's go through a typical workflow. So let's take one of these MIS problems that Hans talked about. Let's say you have a classical problem and you want to find the maximum independent set on some unit of the graph. Just for fun illustration, imagine taking the intersections in Boston and trying to find the maximum set of intersections where you might want to place coffee shops such that they don't interact with each other and take each other's business away. So you take the nodes as possible intersections where you place the coffee shops. You turn those into literally the XY coordinates of the atoms that you program in Aquila. Then you apply the Hamiltonian, evolve the system, choose your algorithm. And then at the end of the day, you measure the atoms again, and where the atoms ended up in Rydberg state, they actually notice they're kicked out and they appear as holes in the original pattern. And then the final result, basically, of these zeros and ones that correspond to whether the atom was there or not tells you whether it was in the ground state or the Rydberg state, and that translates directly back to the solution to this MIS. So the Rydberg excitations correspond to the solution to the MIS problem. This is just kind of to point you in the right direction if you want to start using Aquila. So it's available on AWS. These are availability times as of last week, and there's research credits available for those who want to get started and get their feet wet with it. Another thing that's very useful is we have an open source package called Blockade, which is both an emulator for the Rydberg Hamiltonian that works in tens of qubits pretty efficiently, and it's also an SDK, so separate development kit for actually using Aquila, so you can use it to compose your program, submit it to the device, and get results, analyze the results, and make plots and so on. And so we have two versions of this package. One is in Julia, which is very optimal for these large quantum simulations on the classical hardware. So it's optimized for speed and large qubit numbers. And then we have a Python package, which is a bit more user-friendly and it has a lot more examples and stuff like that for actually working with Aquila. All right, so with that, I want to kind of transition to talking about like, okay, how does Aquila work? And actually, how Aquila works actually kind of, the core elements are the same for many of these neutral atom machines, so we can kind of define kind of more general lessons about how the neutral atom platform works. So the machine is actually, goes through these QPU cycles, you can call them, where most of the time is spent actually preparing the atoms, assembling them into the processor. Okay, so it's about a 200 millisecond cycle for Aquila. It's something on that order for most of these kinds of machines. But before the cycle starts, you have to do the flush of your QA. Okay, so you have to figure out how to make the intensity pattern that the user requested. So this involves some holography optimization that actually takes a few seconds. But once that's done, or if there's already in cache a geometry that's been used before, that just gets loaded, and then off you go and keep doing your quantum computation cycle. Okay, so what does a quantum computation cycle look like? Well, first of all, you load them up, you do optical trap, you get a bunch of cold atoms from thermal vapor, make them into a cloud, and then you load those atoms into the intensity pattern projected into the vacuum chamber with a spatial light modulator. That spatial light modulator is a configurable element that we program once we get coordinates from the user. About half of those sites are occupied, 60%. So we take an image, we see which ones are occupied and which ones aren't, and then on the fly we decide how to steer dynamically movable tweezers that pick atoms from the loaded sites and deliver them to the sites that were requested to be filled by the user but weren't loaded. And so this is an example of a typical algorithm for sorting atoms into the required geometry. Okay? So in this case, the red are the user sites. They wanted this rectangular array of qubits. Those blue are extra sites we add in order to have reservoir atoms. And then after taking the first image, we arrange the atoms to satisfy the arrangement the user wanted. And the efficiency of that process is about 99.5% per site of getting the right decided to the right location. And the user gets to see the subsequent image, or gets the data from the subsequent image, which is which sites that you asked for to be filled did get filled. And so you can post-select on whether there were errors in that or not. And so even though this process is not perfect, you get a chance to kind of throw away the situations where your pattern wasn't perfectly filled, if that is detrimental to the project. Finally, there's a step here of cooling to the ground state and optically pumping the atoms, so initializing them now in the internal state that you need to start with in order to observe the coherent evolution. And then the quantum computation happens. That's only 20 microseconds now of the 200 millisecond cycle, so it's not very good use of time yet. That's going to change in the digital mode of the computer, but for the time being, this coherent evolution under the Hamiltonian program happens over here. And then at the end of it, you take another image, the Rydberg atoms go away, the ground state out of state, and the image actually represents the state detection of the atoms in the ground Rydberg base. And then the zeros and ones corresponding to the detection results go back to the user as the results. Here I wanted to show you our console, actually, and that shows you these 3 frames, these 3 images that get taken every QPU cycle. This is not actually, the images don't go back to the user, only the detection results do. But this is pretty cool because it shows you live operation of the machine in real time. This is basically the cycle time, actually, of the machine. So again, the first image is just loading. The second image is after the atoms were sorted. In this case, they were sorted into an array of atoms that are so far away that they basically don't interact. And then in this case, I'm doing a pi pulse from this frame to that frame, where I'm just transferring all my atoms into the Rydberg state. And as you can see, nothing remains in the last image, just because they're in the Rydberg state, and the Rydberg state appears as dark. All right, so it's the simplest situation. Let's make it a little more interesting. Let's make it pi half pulse. A pi half pulse will create superpositions of all these individual atoms in between the ground and the Rydberg state. And as expected, half of the atoms are in the Russian ground state, as you can see, because you're basically measuring these superposition states. Okay, so we made single qubit superposition states, great. Let's move on to a more interesting example. Let's make some bell states. At this point, I'm putting atoms within the blockade radius of each other, and I'm driving a pi pulse on the two-body oscillation, on the two-body radio oscillation. And as a result, I'm basically creating a state which is a superposition of the excitation, the Rydberg excitation being in one atom of the pair, and the excitation being in the other atom of the pair. And as you can see, in the result on the right, you will only have a Rydberg atom on one atom or the other, but not both and not neither in most cases. So the cases where that's not the case, that's the error in the system. All right, you can get the same result now. Talking about a different kind of algorithm to compare the same thing. You can now apply detuning from large negative detunings to large positive detunings and compare the same bell state. So it's, see the same kind of result on the right. And now, from now on, I'm going to only be talking about these kinds of detuning sweeps as a protocol. Here's an example of where a bunch of qubits are put together into these quadruplets, all within the blockade radius. And you can see that within this 4-qubit cluster, you only have one excitation. Again, this is actually an illustration of a 4-qubit gate if you want. It's a 4-body interaction here that is implemented because that is something that's available to you to program, right? But just position the qubits into a cluster like that. Okay, let's go to an example that's actually more relevant for one of the projects I'm going to describe. So here are 4 chains of atoms where the blockade radius is the size of the next neighbor distance. Okay, so basically what you expect is kind of an anti-paradigmatic chain at the end of the computation, and what you can see indeed is every other atom in the result is excited into the Rydberg state because of this Rydberg blockade. So that's MIS, that Thomas was talking about on a single chain. That's your wire. And then just for fun, here's an example with 256 atoms, as many as you can get basically in this machine, where the atoms are, again, it's the Rydberg blockade radius, it's the size of the next neighbor distance. And you can see here, basically, the arrangement of the Rydberg excitations in that system by looking at where the holes are on the right. All right, so this kind of gives you a glimpse into how Aquila works under the hood and how you go around programming it. I'm gonna move on to describing one of the projects that we worked on with some collaborators, and if you have any questions at this point about how Aquila works, I'm happy to answer. Otherwise, I'll move on to describing these incommensurate phases. And so this is actually a good example of how, one of the ways to work with QuEra. This is a project that, the idea comes from somebody who wants to do something on a machine like that. But, in this case, we want our collaborators wanted to make very long chains, and that was outside of the constraints that we offered through AWS. So we paired them up with scientists at QuEra and helped them do the project directly on the machine. And in this case, it's a project about observing incommensurate ordering on the chains in between kind of 2 well-known phases that Hannes alluded to before. So, Hannes talked about these ordering that is commensurate with the lattice. So, for example, in the case where the spacing is like that on the left relative to the blockade radius, you expect to see a Rydberg excitation every third atom. If you change the parameters by changing the spacing of the ladder, you expect to see Z4 ordering, which is basically Rydberg excitation every 4th atom. Okay, but what about in between? So if you tune in between these 2 regimes, what do you think should happen? Well, if you just look at the average density of Rydberg excitations, you actually see a wash. Okay, but of course, that doesn't mean that there isn't some ordering there, and the thing to do is look at the correlations. And so the correlation we're going to look at specifically is we're going to look at the difference between Rydberg excitation on the bottom row and the top bits along the row. Okay? And so that's the correlation function. And the Fourier transform of that is the structure factor of the Rydberg density wave. And you can now plot the theory, phase diagram from theory of what the phases you expect are. And just like in the phase diagram for just the 1D chains, so the phase diagram for the ladder, this two-chain system, has these Z2 ordering, Z3 ordering, Z4 ordering, Z6 ordering phases, a disordered phase on the left, and then this light green stuff in between is this elusive floating phase, incommensurate phase that we're going to be probing. And the way that we prepare states on this diagram is, the vertical axis is basically tells you about what your spacing is relative to the blockade radius, and then you basically set that for the duration of the experiment. And then the x-axis is the detuning, which you can sweep dynamically during the coherent evolution, and you typically start in a kind of trivial state of all atoms in the ground state, go through the disordered phase, and then sweep from left to right to enter one of these phases that you're trying to probe. Okay, so in all the experiments you basically do adiabatic sweeps from left to right and then stop in one of these phases. Okay, so you arrange the atoms into these ladders. We're going to change the spacing of the atoms, and we're going to change the length of these ladders. Initialize in the ground state, then apply the sweep. So that's your protocol. That's what you would program on Aquila. You literally pulse on the Rabi frequency to a fixed value, and then you sweep the detuning from across the zero detuning point. And one side, all the atoms will be in the ground state, and the other side, all the atoms will be in the Rydberg state, subject to the blockade constraints. Then you measure on a Rydberg basis where the Rydberg excitations ended up for every shot. You collect these bit strings, and then you look at the statistics of bit strings, and you look at the correlation functions of these bit strings. And the correlation function that I mentioned before was basically the structure factor. Okay, so it basically tells you a Fourier transform of the density ordering in the system, of the Rydberg density ordering in the system. Okay, so here's the result for 3 regimes, or 4 regimes. Okay, the left one is the disordered phase, nothing interesting there. Okay, no correlations with the system. Z3 phase and Z4 phase, the second column and the last column, show you this periodic occurrence of the Rydberg density. And this is basically the 2D plot of this correlation function, but here's the average correlation function in the second row. And you can see that basically you see very clear density modulation that's periodic in the spacing of the atom array for Z3 and for Z4. And here the spacing here is, as we discussed before, it's every third atom and every fourth atom over here. And then you do see some kind of pattern in this floating phase. It doesn't look periodic, and that's because it's incommensurate with the spacing of the lattice. But then if you look at the Fourier transform of this density as a function of space, you get the k vector for the Rydberg density wave. Okay, and so indeed you do see very distinct peaks even in the floating phase. So the difference is that in the Z2 and Z3 and the Z4 phases, those peaks happen at 1/3 and 1/4 k vectors. The k vector that you get for the floating phase is 7/24, but it's basically incommensurate with the chain of this length. Okay. Now, as you make the chain longer and longer, of course, there's more possible k vectors that this floating phase can take, and this is what we probe next. So this is the example I showed you before. In this case, you're changing the blockade radius relative to the spacing, and you can see this clear transition from the 1/3 value plateau for the Z3 phase to the 7/24 value for the floating phase to this 1/4 value for the Z4 phase. Okay, that's for chain length of 21. You make the chain longer, and you start to see more allowed k vectors for the floating phase, and then you transition between these different k vectors like plateaus, and it looks like a staircase basically as you add more and more atoms to the chain. And then with the limit, basically, of very long chains, it becomes a continuum of possible k vectors. So that's your floating phase, and then it plateaus at 1/3 and 1/4 of those into Z3. And so you can see this kind of incommensurate phase basically in between your Z3 and Z4 phases. So with that, I want to tell you a little bit about the second project that we did with our academic collaborators, which has less to do with applications of Aquila, like with the floating phases, but more about algorithmic tricks you can use in order to improve your performance, especially if you're trying to prepare difficult many-body states, like hard MIS problems as an example. And so in this case, we studied a pretty simple model system that is kind of exemplifies the problem of this super exponentially closing gap in many-body systems as you try to do adiabatic sweeps into the ground state. And so this geometry is basically this diamond chain like that, where the three atoms on the left basically form an equilateral triangle. And then this is the blockade radius. Red is the blockade radius. Okay, so remind me of the Hamiltonian. Question: what is the ground state of this Hamiltonian in the case of large positive continuums for this diamond chain? Right. So if you use now naive kind of logic that uses the blockade abstraction, you would say, all right, well, just maximize the number of excitations subject to the Rydberg blockade constraint, right? So since the atoms in the doublets along this diamond chain cannot both be excited to the Rydberg state, but atoms along the row are far enough away that they all can be. Actually, the MIS for the system is all excitations in the middle row of this diamond chain. Okay? So this is how we would reason. But when you go and try to measure the Rydberg density up there, you actually see that you're more likely to get the Rydbergs over here on the outer corners of these diamonds. Okay? So remember, the white in the scale is in the middle, and the blue is large, or blue is small, or red is high. So okay, so you actually have oxidations along the sides. So adiabatic, this is what you get if you just try to adiabatically compare the state and cross over across the zero detuning point. And actually, if you think about the real interaction energies, don't constrain yourself to think about only whether you're inside or outside the blockade radius. We realize that, yeah, when you adiabatically sweep, the more energetically favorable state, and somewhere in the middle of your sweep, is actually the zigzag arrangement of Rydberg excitations, because they are further away, and the energy cost that you incur from having them is actually much smaller when they're along the diagonal than when they're along the row, as in this case. So here you are doing your adiabatic sweep. I'll come back to that. So if you actually can measure the probability of this true ground state, you can see that it's exponentially suppressed with the size of this diamond chain relative to the probability of finding yourself in one of these first excited states, which is this zigzag arrangement. Now, if you calculate what is the true ground state of the system as a function of the detuning, the true ground state of the system is the zigzag arrangement until a certain point where the detuning is so large that it counts towards, it counts a lot towards having that extra excitation that you would get by putting everything in the middle row. And so you can see this very discrete step of unity, Rydberg excitation, at some point in your adiabatic evolution, or at some point in the detuning. But you can see that it's a step, so it's actually kind of a first order phase transition that is very hard for the quantum system to cross. 5 minutes left. 10 minutes. Okay. So basically, and the problem with this is that when you first got into this ground state, which has a zigzag arrangement. The coupling to the true ground state with large detunings, which is everything in the middle row, is very low. It's a very large timing distance. It's very hard now to get from this first excited state back to the ground state. And the way you can think about it in terms of adiabatic, in terms of the adiabatic algorithm, is that if you think about the energy diagram of the system, here you are adiabatically following the ground state, and then there's a crossing of this like exponentially, super exponentially tiny gap, and then you just basically run right past it and end up in the excited state. And then you never see the bigger the system is, the smaller the gap, and the smaller the probability of being in the ground state, which is this red star. So now the question is, what can you do to make that better? And Hannes talked about one technique, which is maybe you slow down right around where the gap closes. Now, of course, the gap closes for this particular problem super exponentially, and you have no hope in limited larger systems. One technique that we tried out here is to do the opposite, to speed up and actually quench the system, let this many-body system kind of like oscillate before you get to this closing. So kind of over here. And hopefully you excite enough of the first excited state at this time, such that when you cross through this tiny gap, you actually, first excited state has more population and then ends up being the ground state. And so this is let's go try it kind of thing, right? Is it going to work for the system? And in particular, the kind of quench protocol that we tried was a simple one where you are adiabatically sweeping, and right around where the gap is supposed to close, you jump the detuning, let the system evolve for a little bit, observe this kind of many-body dynamics. Hopefully, that allows you to transition from the many-body ground state before this gap closes to the excited state, and then you jump back and continue your sweep. And first thing you see that as you try to optimize the parameters of this quench protocol, so the starting detuning, the end detuning, and the duration of the evolution, you do see that there's an enhancement of the probability of the true ground state of the evolution. It means that you've actually populated that first excited state before the gap closing with quite high probability. And you see that the optimal quench duration actually is independent of the system size, which is nice, because that you don't have to fine-tune parameters for every particular size of the system. And you can see that the enhancement in the ground state probability is actually quite significant relative to these simple adiabatic sweep protocols, regardless of whether you chose to sweep fast or slow. And so the red and the purple line are fast and slow adiabatic sweep, or fast and slow linear sweep, rather. And then the blue curve over here shows you the performance of the function of system size for this sweep quench sweep protocol. Great, so that already gives you huge improvement in getting to your ground state that you wanted. So what about how transferable it is to other kind of hard many-body problems where you're trying to prepare the ground state? And we actually did try a number of discarded mass instances, and there was no smoking gun. There was some signal there, but I think this is still something that needs to be looked into. If there's a way to generalize this protocol. But the good news is that when we tried this on a 2D extension of this diamond array, so we had the diamond chain before, now it's a diamonds arranged in a 2D pattern like that. Same question as before. What is the ground state of the system? Should be this, based on just maximizing the number of excitations subject to the Rydberg location constraint. But again, if you try to measure the Rydberg density, you get a wash. What we did is we took the same quench sweep protocol that we found for the 1D system, used the same parameters and applied them to this 2D system, except the one thing is that we did vary the duration. And at optimal duration of this quench, you do see a factor of 100 enhancement in the ground state probability for the 2D system relative to the linear sweep, best linear sweep protocol. which is this point over here on the left. Okay, so at the very least you can say that, okay, this protocol or the intuition behind it did transfer from a 1D system to a 2D system. And we'd be very curious to see, how it can be generalized for more interesting kinds of problems that you can encode in Aquila. So this I want to finish and just say that I hope that you're excited about Nickel Atoms to this, and if you want to come work with us, come talk to me or write to us. It's our mission to offer these tools to the world to use and to let people to help people drive their scientific discoveries with this. So thank you. Okay, we have a few minutes for questions.
So thanks, that's a very interesting overview. I'm thinking about your Boston example, proof of concept example. And I live near Boston. It's actually not a planar city, but your example was a planar graph and pretty much grid-like. And so the mapping is simple. You can see how to map this into your 2D grid of atoms. And so I'm wondering about problems that are not planar, and maybe perhaps a little more complicated in their connections. And I'm guessing that's where your chains come in, where you have to connect qubits that are not actually physically adjacent to one another. Is that correct?
Right. So it's true that the unit disk kind of native problem to the Rydberg Hamiltonian without doing this dynamic rearrangement in the middle of the computation, which by the way can be done. It's coming next. So, but in this context, yes, it lends itself the best to geographic problems because they naturally have this planar and kind of unit disk character. Otherwise you do have to use the kind of gadgets that Hannes has. The interesting problem is, okay, the worst case for those gadgets is, n squared. You need the n squared qubits that you actually have nodes at the end. But if you're talking about, okay, maybe problems that are not quite planar geographic, but also maybe not quite general graph, can there be better scaling? Maybe actually, Hannes can comment on that. I don't know if there's some interesting classification in between.
So, thank you for the interesting talk. Follow-up question. We've actually been working with Jonathan Woods since August, trying to crack one of our problems with the machine. And I remember he said something about...
Oh, with Jonathan Woods?
Yes.
Oh, yeah.
And I remember he said something about additional restriction, which I think he didn't go into that much detail, but it's featured prominently across all of your examples where you need to have lines of atoms which are 5 microns away from each other. If you want to squeeze an atom in between the two, then you have to add a new line and sort of spread things out. So going back to Kathy's question about the map of Boston, it's just a question. So one, you probably needed to do some kind of a shifting and stretching and squeezing to sort of meet things on lines, but and the follow-up question is it just a restriction in 1 dimension or also in 2 dimensions? So it has to be on lines vertically and horizontally.
Okay, last question is, there's only restriction in 1 dimension, but that restriction is there and I didn't talk about it. It is a technical kind of outcome of the choice of the sorting algorithm that we have, which makes it go faster, but it has this restriction. It's true that when you have some arbitrary arrangement of nodes in your original problem, you kind of have to coarse grain it to the nearest row that you can have. Or, let me put it a different way, if you don't coarse grain it to the nearest row, the number of qubits that are available to you becomes smaller. Now, this is actually exactly one of those situations where we can sort more general geometries, but it is something that we have to go in and kind of deploy, change it for project by project basis. And this is a good example where if you have some idea and you just can't make it work in the cloud source because of that constraint, for example, you can count work less, and we can probably figure out how to make those geometries. Like, we can definitely just make those geometries. It's just, it could be hard to make any possible geometry once you remove that constraint.
So the picture here on the right is quite a lot of work to put together.
Well,
or is it just by chance?
If you look carefully, this one is on rows. So it is the world map, but like coarse-grained into rows. So, you know, you do get more or less like, you know, still the shape that you want, but you know, it is annoying that you have to do this rapidly.
So suppose we would like to solve a QuEra, right? We saw the example in the previous talk. There you kind of have a bit of a structure where you want to have parts of the variables interact with the other part of the variables, and you have rows and columns. Is there a restriction that you only have to stick to lines horizontally? Or these kind of problems actually translate to also self-imposing on yourself the restriction vertically, or is that not necessary?
So I think for like this crossing wires, actually, there's no reason, like there's no problem with having these things on rows, because you have a very regular structure to the wire, like it's very, you know, regularly spaced. Did I answer the question? I mean, I think, correct me if I'm wrong, but I don't think that the row restriction is a problem for these kinds of encodings for gadgets. And again, on the column, there is no restriction anyway.
Yeah, thank you.
Okay, we're starting to run into coffee break, so let's take further questions offline. Thank you, speaker again.